Hello and welcome to MiniLecture 22 on differential equations. Alright, this is one of my favorite topics in mathematical biology because it makes the world super useful. So, let's think about how we thought about recursion equations. So recursion equations, remember, describe dynamics of everything that went in a circle or a life cycle. So we would have the quantity of something like n of t, and we would calculate what it was in the next time step. And this is useful for describing systems that have a cycle to them, so a life cycle or something that has like a daytime, nighttime cycle. And the result of this is a discrete function. So when we iterate a recursion equation, we get a discrete function where we have the value of the variable n at a bunch of discrete times t. Today we're going to talk about an alternative to this called an ordinary differential equation, or an ODE, that gives us the change in a system as a continuous function at time t. So here, instead of having n of t plus 1, we have a derivative over here on the left-hand side. So we have the change in n at time t is equal to some function of n. Just like with a recursion equation where you have to tell it what the initial state of the system is, you have to have an initial condition down here. But when you solve a differential equation, the solution to a differential equation is a continuous function. So this is a really important fact that I want you guys to really get out of this, that the solution to a differential equation is a continuous function. Unlike a recursion equation where we use these cycle diagrams, when we talk about differential equations, we're going to use something called a flow diagram. What a flow diagram looks like is something like this. So we have our quantity n, and we have some flow into this bucket and some flow out of this bucket. And so this is like the level of water in a bucket. You have some flow in and some flow out, and that flow happens continuously compared to things like this, where this would be like you add a little bit of water to the bucket every day and you take a little bit of water out of the bucket every day. So this describes discrete things, this describes continuous flow. All right, so let's talk a little bit more about ordinary differential equations. An ordinary differential equation is described by this flow diagram where we have the change in state F. So this is the amount of water in our bucket. We have our bucket over here and a bunch of water in this bucket. And then we have the flow into the bucket, which is our I quantity here, the flow into the bucket, and we have the flow out of the bucket. All right, so we have the flow in, and the quantity inside this bucket is our state variable, which we call F, which is the current state of the system at some time t. And just like with a recursion equation, we need an initial condition. All right, so when we combine the ODE, that's this thing over here, and the initial condition, so these two things together, they make what we call an initial value problem, and an IVP. All right, so what do we do with a differential equation? Well, an alternative way to represent that is as a flow diagram, like I've mentioned above. Here I've given you a flow diagram for some population size n of t, and we have three processes going on here. We have birth of individuals, we have migration of individuals into the system, and we have the death of individuals. In order to get a differential equation, we take the left-hand side of the function is the derivative of n. So we take dn dt. So you take the derivative of your state variable, which is the quantity inside of the bubble, and you're going to add all of the terms where you have an arrow coming into the circle. So here we have b n of t plus m, and we have one arrow coming out of that circle. This is this death term, and you're going to subtract all the arrows coming out. So you're going to do minus d n of t. All right, So when we solve a differential equation, what do we get? Well, this is the one thing I really want you guys to remember from this lecture. When you solve a differential equation such as this and the initial value problem where we add the initial condition, we get the solution is a function n of t. So you're solving the function for the population size. All right, so the function for your state variable n of t, and this function is going to be some function of your parameters. In this model, these are all these constants: the birth rate, the death rate, and the migration rate, and your time t. So you're solving for this function. All right. How do we solve for that function? Well, you would actually have to take a whole class on this. It's really useful to do this because oftentimes we can describe how the rates of systems change. We know at what rate things happen, but we don't know what the current quantity in the system is. But if we want to solve these solutions, we'd actually have to take a whole class. Luckily, in this class, we get to solve them, or simple versions of them, in a few ways. The first way we're going to do it is by guessing and checking. So it's always good to know how to check your solutions to your differential equations. All right, so consider the following initial value problem. You have the change in the population size dn dt is some birth minus death, or I can rewrite this side as b minus d n of t. So let's rewrite that initial value problem. You have dn dt is equal to some constant b minus d times n of t. So birth minus death times the population size. And you also have the initial condition, which is the population size at time 0 is some constant n0. All right. If we want to find the solution to this, remember that solution is the function n of t. And so we want to guess a function n of t such that if we take the derivative of n of t, we get out a constant times the original function. So we want to ask ourselves, what function do we know that has the property that if we take its derivative, it gives us back the function times a constant? Well, we know that if we want to get back something in a derivative, e of t is a good guess. So e of t gives us, the derivative of e of t gives us e of t, so that would be a good guess. So let's guess that the function n of t is equal to e to the t. All right, so the first question we have to ask is, does that satisfy our differential equation over here? So let's take the derivative of n of t. So I differentiate this side. We also have to differentiate this side. All right, you guys know what the derivative of e of t is. That's simply e of t. Now, the key here is we want to write the answer in terms of n, in terms of our original function n of t. All right, luckily, this quantity here, e of t, is equal to n of t. We can get that from right here. All right, so we end up with dn of t dt is equal to n of t. All right, is that differential equation the same as the differential equation we got up here? No, it's not. We're missing this constant b minus d. So this does not work. That guess did not work. But we almost got there. We were really close. So let's change it only a little bit. Let's add that little constant up here in the exponent. So now if I take the derivative, dn of t dt, I take the derivative of the other side, d by dt of e b minus d times t. If I take the derivative of that side, you're going to use the chain rule here. This is your u. I'll let you do that chain rule on your own. But what you would get back is b minus d, e to the b minus d times t. All right, once again, we want to write the answer in terms of our original function. Note that this is our original function, and this right here is another way of writing that original function, n of t. So we can rewrite this as b minus d times n of t. Now look at this differential equation. We have dn dt is equal to b minus d times n of t. That's the same as we have here. dn dt is b minus d times n of t. So this is good. We have now found something that solves our differential equation, but it doesn't just have to solve this differential equation. It has to solve this initial condition. So how do we check that if it solves the initial condition? Well, we simply put in t equals 0 into our function here. So let's plug in 0. So we have n of 0 is equal to e to the b minus d times 0. What does that give us? Well, this whole quantity goes to 1. E to the 1, or e to the 0th is 1. Anything to the 0th is 1. So this is equal to 1. Note that this does not satisfy our initial condition because it's not equal to n0. So that didn't work. All right, so if you have something that doesn't satisfy the initial condition, so we have this function here, and it doesn't satisfy the initial condition, we're going to try two different things. The first thing that we can do is we can try adding the initial condition to the outside of the function. The second thing that we can try to do is we can multiply the function by n0. It turns out that those two are good ways of guessing. So let's try this one. Let's check to make sure that it satisfies the differential equation still. We have d by dt of n of t. We take the derivative of the other side, d by dt of n of 0 plus e to the b minus d times t. All right, the derivative of this first term is simply 0 because it is a constant. So that goes to 0, and this term here is going to go to b minus d e to the b minus d times t. All right, rewriting that, we have that this quantity here is equal to n of t minus n0, because if we subtract n0 from this, we get e to the b minus dt. So subbing that in, we have b minus d times n0 plus n of t. Oh, sorry. N of t minus n0. All right. Now, this does not satisfy our differential equation up here, so we no longer satisfy the differential equation. So that is a bad guess. All right, so we don't even need to check if it satisfies the initial condition because it didn't satisfy our differential equation. All right, so let's try the second way of doing this, which is multiplying by n0. If we do that, we gotta take the derivative of both sides. D by dt of n of t is equal to d by dt of n0 e to the b minus d times t. All right, if we take the derivative here, that n0 factors out because it's a constant, so we have n0. Then we take the derivative of the exponential, and we get e to the b minus dt times b minus d. All right, now this quantity here multiplied by this quantity here is our n0, or our nt, so we have our b minus d times nt. This quantity here is our nt. So we end up with d by dt of nt is equal to b minus d nt. So once again, this satisfies our differential equation. Does it satisfy our initial condition? In order to figure this out, we plug in t equals 0. So I'm going to plug in a 0 here. Now, this is our function that we're plugging it into. So we have n0 e to the b minus d times 0. If I plug this in, this quantity goes to 1, and I end up with an n0 over here. All right, so this satisfies the initial condition that n0 is equal to little n0, and that the derivative of this function gives us that back b minus d times that initial function. All right, so we have now found the solution to our differential equation. All right, so with that, I'm going to leave you with this self-study where you're going to use those techniques that we just learned above to try to check the solution to a differential equation.